Welcome to the deep dive. And welcome specifically to our brand new CSWIP 3.1 exam prep series.
That's right.
This is where we're going to help you sharpen your skills.
Yeah.
We want to go beyond just, knowing the answers. We want you to really understand why they're the correct answer.
Exactly. It's about the why.
So today we're diving into some essential multi-choice questions, the kind you'd expect to see on the actual exam.
Just like the real thing.
We'll break them down, explain things thoroughly, hopefully give you that strategic edge.
Yeah.
Our mission really is to solidify your grasp on core welding principles. We're aiming for those aha moments,
Those clicks where it makes sense.
Exactly. The stuff that makes knowledge stick, not just for the test, but importantly for your whole career as a welding inspector.
Absolutely. And what we're really doing here, I think, is equipping you with more than just rote memorization.
Right.
We're digging into those underlying principles, helping you maybe bridge some knowledge gaps that these kinds of questions can reveal. So this deep dive, it's about getting you ready not just to, pass the exam.
Which is important.
Which is definitely important, yeah. But also to feel confident applying this knowledge out there in real-world situations. That's what makes an effective inspector.
That's the ultimate goal, isn't it? Okay, let's jump right in. Our first question, it focuses on something really practical and often pretty challenging in welding.
Okay, let's hear it.
Question 1. Repair welding of in-service plant and equipment may be more difficult than making repairs during initial fabrication because, and your options are, A, the material may be contaminated. B, access to repair area may be difficult. C, positional welding may be needed. D, all of the above. And the correct answer here, maybe unsurprisingly, is D, all of the above.
Right. Often the case with these types.
It is. Okay, so all of the above, it sums it up neatly. But let's think about someone on site, inspecting a repair. What does this combination of factors A, B, and C actually mean? How does it change the game compared to working on, say, a brand new component in the workshop?
Yeah, that's a really crucial distinction to make. Repair welding isn't just technically harder sometimes. It's often a whole system challenge. These three factors, they pile up, they compound, and it demands a fundamentally different approach, often much more meticulous than new fabrication.
More complex.
Definitely more complex. If you connect this to the bigger picture, right, you can see how each one adds another layer of complexity, another layer of risk. It just demands more careful planning, more rigorous execution.
Okay, so let's break that down. Point A. The material may be contaminated. What are we talking about here?
Well, think about stuff that's been running in service. It collects wiles.
Yeah.
Well, all sorts of things you don't want in a weld.
Like what?
Like oils, scale, rust, maybe leftover process fluids, even absorbed hydrogen, which is a really big one for cracking potential.
Right.
If you don't get rid of these contaminants properly, they can lead straight to serious weld defects. Porosity, cracking, lack of fusion.
Nasty stuff.
Exactly. So you need extensive cleaning. Often way more rigorous than for new material. And sometimes you even need special welding procedures just to cope with potential residues.
Okay, that makes sense. What about B, difficult access?
Access. Yeah. Plant and equipment, they're usually designed for how they operate, not necessarily for easy maintenance or repair down the line.
That's great.
So you often find things stuck in confined spaces or way up high or just in really awkward positions.
Yep, been there.
And this isn't just, inconvenient for the welder. It can make it genuinely hard to get the welding gear in there, hard to get the right torch angle or electrode angle.
Which affects the weld itself.
It directly impacts the quality. And productivity, too, of course.
Yeah.
You simply can't make a good weld if you can't physically get to it properly.
Good point. And C, positional welding may be needed.
Right. So during initial fabrication, you often have the luxury, let's say, of moving the component around. You can rotate it, position it, so the welder can work in the flat or horizontal position, which are the easiest.
Downhand welding, yeah.
Exactly. But with in-service repairs, you're usually stuck with how it is. The equipment is fixed in place. So this often means you're forced into complex positional welding. Vertical up, overhead, maybe horizontal fixed. These are way more challenging. They demand higher skill levels from the welder.
And they're slower too, right?
Much slower, lower deposition rates. And crucially, if they're not done perfectly, there's a much higher chance of defects sneaking in. So yeah, it's that combination, the contamination risk, the poor access, the tough positional work that really makes repair welding so much more demanding. and riskier.
It really sounds like repair welding is, well, it's not just a technical task, it's a big logistical puzzle and a risk management exercise all rolled into one.
That's a great way to put it.
I remember hearing about a job on an offshore platform. They had to build this complex scaffolding just to get a welder into an overhead spot. And even then, apparently, the visibility was terrible.
Oh yeah, those situations happen.
It just shows how real those challenges, access positions really are.
Definitely. Understanding those combined stresses is vital.
Absolutely. Okay, speaking of nuanced understanding, let's move to our next question. This one tackles another area where, the details really matter. We're talking about stainless steels.
Ah, yes, the stainless family.
Question 2. With reference to the various grades of stainless steels, which of the following statements is true? Options are A, they are all non-magnetic. B, they all require 100% argon for GMAW.
Yeah.
C, they all have very high thermal conductivity. D, only certain grades can be used for service at very low temperatures. And the correct statement here is D, only certain grades can be used for service at very low temperatures.
Right.
Stainless steel, it's a term everyone throws around, but this question really hits on a common trap, doesn't it?
Yeah.
Assuming they're all identical.
It really does. Forces you to think about the diversity.
Yeah. So why is it that only certain grades work well at low temps? And maybe quickly, what's wrong with those other common ideas in A, B, and C?
Okay, yeah. The key thing here, as you said, is that stainless steel isn't one thing. It's a whole family of alloys, each with its own distinct properties suited for different jobs. And knowing this is absolutely critical for choosing the right material, the right welding procedure.
Crucial for an inspector.
Definitely. So let's knock down A, B, and C first. A, they are all non-magnetic. That's probably the most common misconception.
I hear that one a lot.
Yeah. While the austenitic stainless steel's your common 3 or 4, 316 grades, they are typically non-magnetic because of their crystal structure.
Okay.
Other types, like the ferritic and martensitic grades, think 430 or 410, they are definitely magnetic. And even some austenitic grades can become slightly magnetic if they've been cold worked. So definitely not a universal rule.
Good to know. What about B, the 100% argon for GMAW?
Also false. Argon is very common, sure, as a shielding gas for GMAW, which is MIG welding, essentially. But mixtures are frequently used, too. Mixes with CO2, sometimes oxygen, or even helium. These gas mixes can help improve the bead shape, maybe get better penetration, or allow different transfer modes, like spray transfer. It really depends on the specific stainless grade and what weld properties you're aiming for. So 100% argon, nope, not always.
Okay. And C, the high thermal conductivity.
Yeah, this one's interesting because it's actually the opposite for the most common types.
Really?
Yeah, austenitic stainless steels, the ones used most widely, actually have lower thermal conductivity than regular carbon steel.
Lower.
Lower. And that can be a real headache during welding. It means heat doesn't dissipate as quickly, which can lead to more distortion if you don't manage it carefully.
Okay, so that's A, B, and C debunked. Now, why is D correct? Only certain grades can be used for service at very low temperatures.
Right. This is super important, especially for industries dealing with cryogenic temperatures, think LNG, liquid nitrogen, that sort of thing.
Very low temps.
Extremely low. Now, many materials get brittle, dangerously brittle, when they get that cold. But austenitic stainless steels, again, thanks to their stable crystal structure, generally keep their ductility and toughness even at cryogenic temperatures.
Oh, good for that.
They're often ideal for things like LNG tanks or cryogenic piping. However, and this is the key part of option D, not all stainless steels are suitable.
Oh, okay.
Those ferritic and martensitic grades we mentioned earlier, they can suffer from severe embrittlement at low temperatures. They become like glass, so they'd be completely unsuitable, even dangerous for those applications.
So it really comes down to the specific grade.
Absolutely. You have to know the grade and its specific metallurgical behavior, especially regarding temperature.
So the big takeaway here is stainless steel is a whole spectrum. An inspector needs to be really careful, scrutinize the specific grade listed on the WPS, the welding procedure specification, and check that it matches the intended service conditions, especially if extreme temperatures, high or low, are involved.
Couldn't have said it better. Detail matters.
It certainly does. Okay, that distinction is key. Let's move on. Next question brings us back to carbon steels, CMN steels, and a very specific concern in the weld area.
All right.
Question 3. Which element has the greatest effect on the HAZ hardness of CMN steel? Your options. A, molybdenum. B, chromium. C, titanium. D, carbon. And the answer is D, carbon.
No big surprise there, maybe.
Perhaps not. Carbon often seems to be the main character, doesn't it, when we talk about steel properties?
It really is the dominant player for hardness.
So why? Why does carbon have such a massive effect on the hardness of the heat-affected zone, the HAZ, in these carbon-manganese steels?
Yeah.
And how does that link to weld quality and, potential problems?
Well, carbon is fundamentally the primary hardening element in steel, full stop.
Okay.
Now, when you weld that area right next to the weld metal, the HAZ, it goes through a really rapid heating cycle, followed by quite rapid cooling as the heat dissipates into the surrounding metal.
Right, that thermal shock.
Exactly. And this rapid thermal cycle transforms the microstructure of the steel in the HAZ. Now, if you have a higher carbon content in that steel, it significantly promotes the formation of very hard and unfortunately often brittle microstructures. The main one we worry about is martensite.
Martensite, heard of that?
Yeah, it's a super hard, often needle-like structure. Higher carbon means more potential to form martensite, especially if the cooling is fast.
And hard means brittle.
Hard often means lower toughness, yes, more brittle. And this dramatically increases the hardness of the HAZ, which in turn makes that zone highly susceptible to cracking, specifically the dreaded hydrogen cracking.
Ah, hydrogen cracking again.
Yes. Now, the other elements listed, molybdenum, chromium, they are important. They affect hardenability too, meaning how easily martensite forms deeper into the material. But in typical CMN steels, their direct impact on the peak hardness right there in the HAZ is much less dominant compared to carbon's influence on forming that hard martensite layer right near the weld.
And titanium.
Titanium plays a different role, usually. It's a strong carbide former, often used for grain refinement or stabilizing things, rather than having that direct primary hardening effect on the HAZ in the same way carbon does.
Got it. So carbon is king for HAZ hardness here. If that's the case, what's a practical scenario? Say you're an inspector, you look at a WPS, and you see a higher carbon level. What should immediately pop into your head? Is it really like a big red flag for potential cold cracking?
Oh, absolutely. Huge red flag. If you see a WPS for a CMN steel with a higher carbon content, or as we'll discuss soon, a higher calculated carbon equivalent value, your internal alarm bell should definitely be ringing about potential hydrogen cracking.
Okay.
You'd immediately be double-checking, scrutinizing the specified preheat temperature, the maximum inner pass temperature, any requirements for controlled cooling rates.
Why those things specifically?
Because the goal of preheating and controlling interpass temps is to slow down that cooling rate after welding.
Slow cooling.
Yes. Slowing it down does two crucial things. It gives any hydrogen that might be present more time to diffuse away harmlessly, and it makes it less likely for those hard, brittle, martensitic structures to form in the HAZ. You get softer, tougher microstructures instead.
So managing carbon, or knowing the carbon content, is fundamental to preventing cold cracking.
Absolutely fundamental for ensuring the structural integrity of welds in these steels.
Okay, that makes perfect sense. Carbon is the big player for HAZ hardness in CMN steels. Understanding that is vital. Right, our next question moves us into the world of mechanical testing specifically, a very common test used for weld procedure qualification.
Okay, testing, important stuff.
Question 4. A transverse tensile test from a weld procedure approval record test plate is used to measure. Options are A, tensile strength of the weld, B, tensile strength of the joint, C, stress strain characteristics of the weld, D, stress strain characteristics of the joint. The correct answer here is B, tensile strength of the joint. Yes, the joint. Now that distinction between weld and joint, it sounds subtle, but it's really critical here, isn't it?
Absolutely critical, yeah.
Can you walk us through why this specific test measures the joint strength and why that particular measurement is so important for qualifying a procedure?
Sure. This really gets to the heart of understanding the overall structural integrity that the welding procedure provides. The key is in the name, transverse tensile test.
Transverse meaning across.
Exactly. The test specimen is cut across the weld. So when you prepare that specimen and pull it in a tensile testing machine, the piece being tested includes not just the weld metal in the middle, but also bits of the heat-affected zone, the HAZ, on both sides, and some of the original parent or base material on either side of that.
So it's got everything in there.
It's got the whole system right across the connection. Therefore, the test isn't just measuring the strength of the filler metal that was deposited. Instead, it measures the overall tensile strength of the entire welded joint. It's basically designed to find the weakest link across that whole transition weld, HAZ parent metal.
Whichever fails first.
Precisely. It verifies that the combined structure, as produced by that specific welding procedure, meets the minimum required strength for the application. It's a fundamental check on the procedure's capability to make a sound, strong connection overall.
So if you just wanted to know the strength of the weld metal itself,
you'd use a different test, typically an all-weld metal tensile test, where the specimen is machined entirely from the deposited weld metal, usually taken along the length of the weld, not across it, or sometimes a longitudinal tensile test. But the transverse test is about the joint.
Okay, that's a really important distinction to grasp then. Especially for anyone involved in inspection or qualification, it means you're not just looking at the quality of the weld bead itself in isolation.
No.
You're verifying the performance of the entire assembly right there at the connection. It's like a system check, ensuring the whole thing holds up.
Exactly. Does the procedure produce a joint that's fit for purpose? That's what it tells you.
Very clear. Okay, let's tackle our final question for this session. And this one loops back nicely to something we touched on earlier, carbon's effect on steel.
Bringing it together.
Question 5. Carbon equivalent values, CEV, are used to determine how to avoid the risk of options A, hydrogen cracking, B, lamellar tearing, C, solidification cracking, D, weld decay.
All right.
And the correct answer is A, hydrogen cracking.
There it is again.
Hydrogen cracking, yes. We talked about carbon affecting HAZ hardness, and now we're explicitly linking this thing called carbon equivalent value, or CEV, to preventing hydrogen cracking. So what is CEV, and why is it specifically a tool for heading off this particular type of cracking? Why is it so critical for an inspector to understand?
Right. This is where we move from just knowing carbon is important to having a practical, calculated value that directly informs our welding practice. It's a really critical tool for you as a potential welding inspector.
What does it calculate?
The carbon equivalent value, CEV, is basically a formula. It takes the percentages of various alloying elements in the steel. Carbon is the main one, of course, but it also includes manganese, chromium, molybdenum, vanadium, nickel, sometimes copper.
The whole gang.
Pretty much the key players that affect hardenability. And it combines their effects into a single number that represents the steel's overall tendency to harden.
Okay, so it quantifies hardenability.
Exactly. A higher CEV means higher hardenability, which means, going back to our earlier discussion, the steel is more prone to forming those hard, brittle microstructures like martensite in the HAZ when it cools quickly after welding.
And those hard structures plus hydrogen.
Plus stress. You always need stress too. That's the classic recipe for hydrogen cracking. Remember, it's also called cold cracking or delayed cracking because it can happen hours or even days after the weld looks fine.
Right, the delayed aspect is scary.
It is. So the CEV calculation becomes a predictive tool. It directly guides crucial decisions on how to weld that specific steel safely. Primarily, it helps determine the necessary preheating temperature and sometimes the maximum inner pass temperature.
To slow the cooling again.
Precisely. Higher CEV generally means you need a higher preheat to slow down that cooling, allow hydrogen to escape, and avoid forming too much martensite. It's all about mitigating that risk of hydrogen cracking before it starts.
And just quickly, why not the other options? Lamellar tearing.
Lamellar tearing is more about the steel plate itself having poor ductility in the through thickness direction, often due to inclusions. It's related to joint design and material quality, not directly predicted by CEV in the same way.
Solidification cracking.
That happens during freezing in the weld pool itself. It's driven by weld metal chemistry, things like sulfur and phosphorus content, and how much restraint is on the joint. Again, different mechanism, not CEV's main job.
And weld decay.
Weld decay is totally different. That's a type of corrosion specific to certain stainless steels, caused by chromium carbide precipitation at grain boundaries. Nothing to do with CEV in carbon manganese steels.
Got it. So CEV is laser focused on predicting and helping prevent hydrogen cracking in hardenable steels.
That's its primary function, yes. It's a numerical warning sign, driving practical actions like preheating.
A vital predictive tool for inspectors and welders. Okay, fantastic. So wrapping this up, what does this all mean for you listening? Well, we've covered some pretty crucial ground today, haven't we?
We have, from the real-world messiness of repair welding to the surprising variety in stainless steels, the key role of carbon in HAZ hardness, and how we use CEV to tackle hydrogen cracking risk.
And remember, really understanding the why behind these answers, that's what truly empowers you, not just for the exam, but day to day in your career as a welding inspector.
Yeah.
We really hope this deep dive into these exam-style questions has given you some valuable insights, maybe clarified a few things, and definitely strengthened that foundational knowledge.
And maybe it raises an important question for you to think about after this.
Oh.
How might this deeper understanding, going beyond just, memorizing option D or A, how might that fundamental grasp actually allow you to spot potential issues before they become problems out in the field?
Good question.
How can it help you ensure quality, prevent costly failures, and ultimately ensure safety in real-world welding scenarios? That's the real value.
Thinking like an inspector already.
That's the goal. So keep exploring these ideas, keep asking questions, keep connecting the dots in your mind. That really is how you build true expertise.
Excellent advice. Well, thanks for joining us for this session of our CSWIP 3.1 exam prep series. Until next time, keep learning, keep growing, and stay sharp.